And here we have a model example that you can have, for example, in your RV, in your camper van, or in your garden, or for example on your cottage that is somewhere remote, or anywhere else. And this is approximately how big solar panels you would need to fully charge the battery in one sunny day. So what you need: solar panels, some protection, and an MPPT converter that would then charge your battery, your TimeUSB 100 amp hour battery. From this battery you can then, for example, charge your power tools. That's great. Or you can buy a fridge, this one is ViVor, and you can store, for example, milk. Or you can buy yet another compressor fridge and store, for example, meat. Or even if you don't have a compressor fridge and you have some old, junky somehow Peltier fridge, well, this one is heavily modified, as you can see, then you can as well use this one. This is a mod done by me, as it gains some efficiency, but it looks very horrible, I must say. But also, if you would have any mains powered appliances that cannot be powered from DC 12 volts, you can then use any power inverter, for example this one, that would take your DC voltage and convert it to 230 volts or whatever you have in your socket. So you can then power, for example, an air compressor, you can then power a heat gun or your desktop PC. I welcome you to my another video review. I was contacted by TimeUSB company if I could record a review on this TimeUSB 12.8 volt 100 amp hour battery, and I have agreed. And what is an extra is this English video for the worldwide audience, as I supposed most of you wouldn't understand my Czech video. If you are a resident of European continent, then TimeUSB for Europe is available in English or German, and their warehouse is in Poland, so some Grzegorz Brzęczyszczykiewicz guy with his bobber probably takes care of the shipping. For EU residents, the price is 200 euros. Now about the cooperation between me and TimeUSB. We have free cooperation, so they have sent me this product for free for a review, and I must record and release a review. We agreed on just Czech review, but I am as well doing this English review too. There is no money involved, and I do not have any affiliate or commission from sales. TimeUSB may be able to track the link, and I am able to do so too. I am not rewarded in any means based on sales, etc. TimeUSB company also doesn't make me say or not say anything or do or not do anything. Now, how have I tested the battery? I have run it through some cycles to let it sit and then begun testing the capacity and stored energy using mainly 4-wire method, and that would be for 10 up to 170 amperes of load. I have as well measured the capacity when the battery is stored at -20 degrees Celsius and checked whether the BMS allows it to charge. Of course, I have as well used the battery in real case scenarios, mainly for lighting when working. I have then cut the battery open Get the leap. Measured cell's internal resistance, measured voltage loss on parts on insides, then figure out how the balancer behaves and measured the balance current. And we are gonna as well look inside, and I am gonna show you what I like and what I don't like. Oh yeah, the battery. I have already opened it, and I like to do all my research and testing prior to recording the review, so that the informations here would be comprehensive and well integrated into the flow of the video. Recording a log of each test I perform would make this video 10 hours long, and it would gradually gain some information and experience while making the previous experience obsolete or even untrue. So that's why I first test everything, then prepare a script, which I'm reading right now, and then record a video. So now the battery is already opened. As you can see, my hands have been here, so that's why it's it's taped together. When you receive the well-packed battery and open the box, there is some attachments. We got these insulation caps on terminals to protect them from accidental short. Then a set of stainless steel M8 bolts with integrated washer and split washer, and the head takes standard 13mm wrench or PH3 screwdriver. Additional set of stainless washers is included, but I don't know why actually. Then there is insulation caps, which I recommend using as they prevent 80% of accidental short circuits. Shall something fall on your terminals, then it lands on this plastic insulation and nothing happens. If you wouldn't have them there, then well, good luck welding something on your main terminals. Of course, then there is the BMS that should disconnect the output. I have as well received a ton, maybe 2 tons of stickers. So there is 3 of these stickers. I don't know whether you would get them too. I don't really know. So 3 TimeUSB stickers on A4 format. Then this 1, 2, 3, 4, 5, 6, 7, 8 stickers, smaller ones, and then 3 stickers with this. We also have here some pamhlets. They are in English and also in Deutsch, but as I have forgotten my helmet and my uniform, therefore I cannot read German, so let's stick to the English manual and the English pamphlet. The pamphlet is just some general instructions and nothing extra special. But manual, well, that is something. Let me adjust zoom on my Sony Xperia from 24mm to 40mm, sounds about right. And let's explore this manual. All the parameters of the battery can be found on TimeUSB webpage or in this manual. The recommended charge current is here just for longevity purpose, as lithium ion and LiFePO4 cells, they are best charged with 0.2 C current, which is 0.2 times 100 amp hours is 20 amps. It's very easy, you just multiply the capacity, the 100 amp hours, where it is here, you multiply the capacity with the C number. So 0.2 times 100 is 20, and then the C means that you just remove the H and you have just amps. I think that TimeUSB could include some of the nominal and maximum parameters on the battery itself. Just some quick reference data, some production label with voltage levels, with recommended and maximum currents, with temp ranges, etc. This all should be written on the battery itself as well. This is just full of warnings and warnings. If you wanna read through them, just pause the video or download the manual in PDF from TimeUSB webpage, which I like, as they provide you with any manuals on their page. Here we have, that's the contents. Here we have some battery parameters and they are in detail. Take the internal resistance with a grain of salt, as LiFePO4 cells have different resistance at different voltage levels, and moreover, there is BMS in the path, which is just full of semiconductors. You cannot measure the internal resistance when there is some semiconductors in the way. Then a cycle IF. Cycle IF is supposed to be over 4,000 times, which may sound insane, but it is in LiFePO4. So yes, this may and probably will be true, as the cells inside I'm going ahead of myself, but the cells inside are good quality, so they will surely survive more than 4,000 times. Here is some maximum and recommended parameters all sounds reasonable, and I think is true. Well, apart from the max discharge current, 1 second, this is extremely high value. This would be able to start a small gasoline vehicle. It's not made to start any cars, but this would be able to start a car with smaller petrol engine, like 1.2, 1.3 liters, something like that. It makes sense that they write here some temp ranges and that they separate charging and discharging. My advice would be to charge it between 5 degrees Celsius to 30 to prevent higher damage to the battery, and only charge outside of this range when you push small currents. Never ever shall you, however, charge outside of the claimed range. You would destroy the cells below 0 degrees Celsius. So it's good they wrote it here. Some things to know. Well, all of these make sense except for the position. You can run LiFePO4 cells even upside down. It doesn't matter to them. The electrons are surely not gonna fall out. Neither 3, neither new Vegas, neither 4. So no fallout. This capacity rule, it is true for all lithium technologies, but with LiFePO4 you unfortunately cannot determine where you are at 50% unless you get a coulometer, or use some timeout charging, or use capacity limit on your RC charger or DC load. Yeah, so you never know when you are at 50%, but yeah, this is true. The solar panel recommendation is definitely okay. If you live in mild climate, just take the watt peaks of your solar panel and multiply the number of watt peaks, multiply them by 4 or 5, and you have daily production in one sunny day in mild climate. The general rule of thumb is to have solar panels 1.5 times stronger than what you need, and to have battery capacity high enough to get 2 to 3 days of full autonomy, which means getting 2 to 3 days of bad sunlight and you still have power, you still have juice. These recommended charger settings come really handy, but please limit the charging voltage to less than 14.4, maybe even 14.2, maybe 14. This way you would prevent the BMS overcharge protection kicking in, as it could result in your MPPT charger damage. So float 13.6 and absorption, bulk, topping and equalization set to 14.4 max, but I would set for 14.2, 14.0, something like that. That's because the MPPT chargers, these chargers from solar panels, they don't like when you disconnect the battery from them when they are charging the battery. So that means when the BMS would disconnect the charging MOSFETs, then it would act as if you disconnected the battery physically. And the MPPT controller could as well explode using some special effects, or it could just die peacefully. Yeah, but there is 50-50 probability that you will be with a damaged or destroyed MPPT charger. Then there is battery charger, so that is about the charging. This is the voltage curve. Well, it goes slightly higher in here in the end. Cable sizing. This is just a quick reference, and moreover the entire world, with the exception for North America, uses millimeters squared, not American wire gauge. So they go as following: 1 millimeter squared, 1.5, 2, which is only for Japan I believe, 2.5, 4, 6, 10, 16, 25, 35, 50, 70, 95, 120, 150, 185, 240 and 300. Please remember that if you would want to use 300 mm squared wire, you would need 1 man per 2 meters of the cable to carry it around. But with inverters we usually stick to 25, 35, maybe 50 mm squared, which would be between 4 to single zero gauge. If you want to use extremely powerful inverter on 12 volts, or if you would need to lay down like more than a meter of cable between the battery and the inverter, please install mobile app called ElectroDock. Formerly it was ElectroDroid, and there you can enter all the aspects, and it tells you the power loss on the wire as well as the voltage drop. Keep the voltage drop below 250 millivolts for 12 volt system and 500 millivolts for 24 volt system. If you need some quick reference for mains cable sizing, refer to German standard DIN VDE 0100, which specifies maximum load and maximum circuit breaker for each wire cross section, and that is for 3 different cooling scenarios. So to be honest, this reference table, take it with a grain of salt. It's not exactly applicable to even extra low voltage use case like TimeUSB 12-volt battery, as the voltage drops would be extremely significant on these wire thicknesses. I would advise take these amps and multiply them by 0.75, and that is only for shorter wires, maximum 1 meter wires. If you would get like 1.5 meter, then multiply them by 0.5. These ampacities. Insulating gloves, okay, you don't need insulating gloves when dealing with 12-volt batteries. Only if you would make a 48-volt system out of them, then yeah, but 12-volt or 24 volts, they are safe. If you are in a normal environment and you are not in some bathtub or something like that, then 12-volt and 24-volt is absolutely safe to touch. The voltage balancing before connection must be done not with a solid wire, because you would then be heating the solid wire quite rapidly and maybe even glowing red, but with a bulb at first. So the bulb would limit the current, and both batteries must be at 100%, because below 95% the batteries will have whatever voltage, which doesn't depend that much on state of charge. So always do the top balance and always limit the current. First a bulb and then a thin wire. This graphics comes from my Czech video. Well, the parallel bus bar recommendation is good. Always use some bus bars for connecting more than a single battery, and I would add a fuse on plus pole of each of the battery, just to be safe. Well, this is wrong. By doing this, you will have more reliable the balance interconnections compared to the series interconnections. And guess where the main current flow is? The main current flow is here through these wires, then through these yellow or orange wires, and then through these red wires. This is the main path of the current flow. There is almost no current flow in these parallel interconnections. Neither of them. There would be like few hundred milliamps, maybe some amps after some time, but there is no current flow. So it's a bad idea to first connect the interconnections that wouldn't be actually loaded. Oh, for 44 millimeters, that is too high still. 40 millimeters, oh, 38, come on. 41, okay. Nobody cares, you don't see it either. So these interconnections, they are not crucial. What is crucial is these interconnections from the bus bars and these orange ones. So always make these current paths from thick wires. If you would omit these balance interconnections, mainly these, then you would need just one fuse per one most positive battery. So fuse on cell. So fuse on battery 1, battery 3, battery 5 and battery 7. Shall you use these interconnections, then you would need a fuse on each battery in the system, which is 8 batteries in this case. So it's a bad idea to use these interconnections. And moreover, shall some of the batteries die? For example, if number 6 would die, then the circuit itself would be out of balance and it would perform poorly. And for you to find out which of them is bad, you need to turn off the entire system, take it all apart, and then you will find out with your multimeter that battery number 6 is dead. Whereas, if you would not use these interconnections, then if battery 6 would die and you would encounter some low capacity of the pack, then all you do is just disconnect the first series, test it, okay, connect it back. Disconnect the second series, test it, okay, it's good. Then connect it back. Disconnect the third series, oh, it's bad. Yeah, so you leave it disconnected, and then you take care of the bad battery, while the rest of your system, the 1, 2, 3, 4, 7, 8, are still operational and your system is still working. Rebalance every 6 months, well, only if you don't let the batteries do their top balancing or if you don't have a 12-volt battery pack balancer. If your system would be overpaneled and batteries would be fully charged at least an hour a day, chances are you wouldn't need to balance them at all. Well, yeah, this info is very important, and mainly the 0-volt charging function, which is very often a huge problem finding, and you would end up using a laboratory power supply. The direct panel to battery connection is also a good idea, but it works the best if your panels are 12 volt, which means around 15 volt MPP. If you would have some panels with 35 VOC or something like that, then the BMS may not even connect to the charging MOSFET. But yeah, this 0-volt charging function is really crucial when you have a discharged battery. This is the end. So yeah, the manual is pretty nicely informative. Some info is oversimplified here, some should be shifted, but generally speaking, well done manual. Actually, not many Chinese products come with this nice manual, even with colorful pictures. I mean, it has colors, look at this. Yeah, and the outer shell is of wax paper or something like that, so very nicely done, this manual. I must say that I am impressed. This chapter of the outer look is gonna be very fast. Here you can see my precision cut. I mean, if I wouldn't tell you about it, you wouldn't even notice, would you? Looks fresh from the factory. Well, apart from the ugly area I must take care of, and the fact that I need to find a way to hold it together somehow better than this. I don't know. The battery is of a supposedly standard size of group something, I don't know. This is not a thing in Europe, as we use DIN sizes with a little foot at the bottom. Yeah, but size-wise it's the same displacement as normal 100 amp-hour lead-acid batteries for caravans and RVs, and therefore it will fit a tight compartment without any problems, and it wouldn't wobble freely. The terminals are made of massive aluminum flange, which is probably epoxy glued into the lid, and both ends have M8 thread in them. They as well use stainless steel M8 bolts. Great stuff. Then we got the carry strap here, which is removable. The dimensions and weight can be seen on the screen, as I don't consider them to be a huge game changer that would require more minutes of this video. So, let's not tense you any further and open the battery to see the insides. The BMS, well, I have torn it apart, so this is not TimeUSB problem, this is me doing that. The BMS is as usual in the minus potential pathway, which is standard and comes from most transistor needs. Power Plus is done with silicone insulated wire that has approximately 20 to 25 mm squared cross-section. The cable lugs, they are the better Chinese type, which is somehow massive copper core with chemical tin plating. Here in Europe, the industrial cable lugs are much more massive compared to this, but well, this is still a market where the price matters the most, and few grams, who cares if it holds? I mean, some batteries even use sheet metal lugs, and absolute worst are the iron or copper plated plugs. These are awful. So what we see here is probably the best they could get in China, and this is completely enough, I would say. The silicone wire is then put into a fiberglass sleeve for that ultra high temp scenarios. Like for example, if your caravan would burst into flames from the gas piping, then this battery wouldn't short itself and the insulation would hold even at 600 degrees Celsius. The overall plus path resistance is 386 microohms or 0.386 milliohms. The battery minus is divided to 3 silicone insulated copper stranded wires with nickel plating. That is to spread the current across the PCB more homogeneously. Shall there be just a single wire going to single spot, then the closest MOSFETs would burn and the furthest MOSFETs would just rest. So nicely done. The minus pathway has total resistance of 1.29 milliohms, of which the majority is the BMS, so expect lower values for higher currents. The BMS is therefore as well the place where most heat would be concentrated when loading the battery with high currents. I have calculated the total losses on the internal wiring as following: 17 watts at 100 amps, 67 watts at 200 amps, and 268 watts at 400 amps. This would suggest the approximate maximum long-term current draw of circa 120 amps approximately, which is a huge reserve as the battery has long-term maximum claimed current at 100 amps. And generally speaking, these batteries, they do not encounter over 20 amps mostly. Shall you have some power-hungry equipment that would would take 80 amps and more for a few minutes, I recommend on using some 1 degree thicker wires to cool the battery down more effectively, prolonging the battery life. Just like in my example, for battery testing with inverter, I am using 50 mm squared wires that are 40 centimeters long. At 100 amps, they drop just 28 millivolts, losing just below 3 watts to heat, which is great actually. And they even cool down the minus pole, because the 50 mm squared wire I was using, it was hottest at the place where the minus pole is, so it was effectively cooling the BMS. The voltage sensing and balancing wires are done the normal way, and some premium manufacturers would put them in channels or wraps. Some low-quality manufacturers leave them over sharp edges, over battery poles, etc. Here it is somewhere in the middle. Not beautiful, but safe. What I like here is that they have markings on all the cables here. They have sleeves, which make any user measurement and diagnostics much easier. Using these wires, the BMS monitors voltages of each cell individually and then decides on turning off either the discharge MOSFETs or the charge MOSFETs. They are also used for balancing, and the balance, that is a weak point. This is just a very basic BMS with passive balancer that draws just 42 milliamps from single cell or 26 milliamps from 2 adjacent cells. This is on the border. In my opinion, this would be enough if the battery would remain at charge state for prolonged periods of time, or if you wouldn't overload them every now and then. Shall you load it heavily, regularly, or not keep it at charge state for any meaningful time? The current from the balancer may not be sufficient to keep them the same. At least the BMS can balance more cells at the same time. The temp sensors or contacts are just two. One of them is on the BMS and one of them is on the cells. They are not of a metallic type, but bimetallic type. So they just do on-off stuff around the nominal temp. This is just for overheat protection, and as it is basic, it's still there. Fortunately, this type of the most primitive temp protection has one huge advantage, which is its scalability. Just add some more bimetals in series and that's it. They are gonna work. Even if you change them for another value. If you would change this one for a different value one, it would work. No programming, no Bluetooth mobile app, just wiring and it will work. Simple logic. As there is just two high temp discharge bimetals, this BMS doesn't seem to have a low temp protection, which I have tested the proper way, and more about it later. All the bolt connections, they are glued with silicone to prevent loosening them. Now let's flip it so we see the cells terminals, and here we have this foam. And what I like is that they have these cutouts here, so they wouldn't hide the vents. So in case of fire, the vents can easily do their usual stuff. Poof. Yeah, poofy vents. Nice to see them uncovered and able to do their job. The valves do poof thing. They are clean and they are not penetrated from the inside. And the QR codes, they seem to be original, as they are not laser erased but straight on original aluminum case. So these are from the factory and probably brand new. The cells are made of company Gotion, which is some higher mid-range cells. They are great at longevity, but they may sometimes have some little problems with internal resistance. So they will hold for pretty much a very long time. The cells, of course, they have fiberglass boards between, the red thing, which is mandatory to prevent short circuit because the blue wrap isn't really insulating properly. For cell compression, they have two plastic straps. Let me just flip it this way. Okay, so these plastic straps, which is enough to hold even several people, and the corners, they are reinforced That's how I like it. Nicely done. What is a little problematic here is a lack of pressure plate that would homogenize the force across the entire surface of the side. Personally, in this case, I use 2.5mm thick steel plates, and it still isn't perfect. So I'm thinking about using two of them, 5mm thick steel. So this means that over time, the cell 1 and cell 4 are gonna inflate a little, like 2mm approximately, and they would have some lower capacity, so they would be often balanced, but nothing really bad, just the capacity drop is gonna be a little faster in these two. The cell interconnections are welded on aluminum sheets with dilatation stress relief in the middle. All the threaded holes for bolts, which means the main power connections as well as the balance connections, they have push-in steel nuts, which is great. I mean, if they would just tap a thread in the aluminum piece, then the thread would be too soft, so steel nut inserts are very fine, and I like to see that. Let's measure the cell's voltage. Of course, we must do this. When I was testing the balancer current and behavior, I was actually disbalancing them with my laboratory power supply. So let's see whether they are in balance or not. We have this multimeter here. I'm gonna do a review on it, but it's gonna be only on my check channel, I suppose, because I don't have that much time. 3.502, 3.503, 3.500, slightly less, 3.501. If you would want some quicker comparison of these cells and not have to remember the values, then I have a trick for you. If your multimeter is able to do relative or a rel, then do that. Yeah. Now this is the reference value and this is the difference value. So the difference here is 1 millivolt. Difference here, 3 millivolts. Different here, 2 millivolts. So yeah, they are very nicely balanced. Actually, almost perfect. Well, it is perfect because this instrument isn't that much accurate. So yeah, they are perfectly in balance. So at least right now, the balancer current is enough. Yeah, and it is able to balance two cells at once, which is okay. But in 10 years, if the battery would be overloaded, then you would need a more powerful balancer. Now, about my testing. As you probably know, I do not record my tests on video. As such, a video would have like 10-20 hours. So instead, I take photos of these tests and mainly present the results, including their interpretation. So let's begin with discharge capacity. I repeat that I have run the battery through a few cycles, so the capacity would at least somehow stabilize. Well, in LiFePO4, the capacity stabilizes over like 50 cycles or so. So yeah, the 5-6 cycles I have done, it's not that much, but still better than nothing. Then for currents of 10, 20 and 30 amps, I measured the capacity and energy very accurately using a 4-wire Kelvin method, which compensates for voltage losses. Both the capacity and energy were within the specifications. At 50 amperes, I had to use my uncalibrated RC charger, which has reported slightly less than advertised, but as I have never calibrated it and adjusted it, as it is impossible unfortunately, take it with a grain of salt. All the higher currents were measured using 230 volts inverter, while voltage and current were measured and datalogged with Hioki CM4375-50 AC/DC clamp meter. I have a review on this one. All the generated test report data are available in the video description for free for download. At 80 amperes load, which is approximately a 1 kilowatt load, the battery provided 99.9 amp hours and 1244.9 watt hours. If we would be at the borderline of the maximum long-term specifications, the battery is still up to the claimed parameters, just 0.1% lower, which is actually nothing. The 100 amp current load was measured using regenerative discharging, and I still got 99.9 amp hours, which is actually very nice. I mean, the 100 ampere is 1C load. It's a huge drain, and it still manages to keep the nominal capacity. Well, LiFePO4 batteries should be loaded with 0.2C, maximum 0.50 long term, and up to 1C just occasionally. but it seems that this battery just doesn't mind it, which talks a lot about the quality of the cells inside. Anyways, I have already ordered some laboratory loads, so my next LiFePO4 AccuPack tests are gonna be more accurate and more comprehensive, but these sort of beta tests still talk a lot. I have as well tried to overload the battery with 2 kilowatt load. That was 173 amperes, which is 1.73 C, or 173% load. Life is easy when you have even 100 amp hours. Calculations don't take any time. The battery lasted 12 minutes until the BMS has overheated and the bimetallic temp switch has ruled to disconnect the battery. Having such a hot battery is not optimal, so naturally I have put it in my car fridge that was set to minus 20 degrees Celsius, and I let it sit there for 3 days straight to simulate some freezing winter, like when using a caravan in winter and having the battery in the front compartment, which is not thermally insulated, nor is it heated from your gas or diesel heater. Then, after 3 days in minus 20 degrees Celsius, I have just connected the cables to the battery. One cable is current, that is the one with water droplets, as it got warm slightly, and the second cable is voltage sense. As this line is not loaded, the wire began freezing from the inside. So you can be sure that I wasn't cheating based on this freezing, and the fridge was running all the time, even when the capacity was being tested. Testing current was 10 amps. Measured capacity, was 97.654 amp hours, and energy was 1154.83 watt hours. So very close to the nominal, and actually beautiful. It has almost the nominal capacity, even when frozen to minus 20 degrees Celsius. Now, being 97.7 amp hours short, the battery was discharged and frozen, so I have attempted charging it with just 1 ampere. The BMS has allowed me to do so, which I have immediately stopped, of course, to prevent damage to the cells. Any lithium cells, which means LiFePO4 or lithium ion, they must not be charged below freezing point, and I would advise to charge them only above 5 degrees Celsius for longevity. This doesn't apply to special low temp cells, but these are rare to find, and because of their price and lifetime, they are only for specific use cases like for military equipment and such. Next test was the internal resistance of the cells inside. DC loading resistance test is generally more accurate as it provides more reliable data, but LiFePO4 do not have this consistent across their charge gradient and also in time. So I have resorted to publishing just standard AC 1 kHz testing results, which you can see here on the screen. These Gotion cells are good quality, but they lack in widespread of internal resistances, which is as well in this case, approximately 10.4%. The values go from 217 up to 241 microohms, or approximately 0.2 milliohms. The undervoltage protection of the BMS stands at 2.5 volts per cell, which is normal, and overcharge protection disconnects the charge MOSFETs when at least one cell reaches 3.60 volts. I must admit that 3.60 is slightly conservative, and it will surely help preserve the cell's life a little bit better than the standard threshold of 3.65, which is usual. So here it is, my 2 months of testing this battery and actually inventing ways on how to perform the test is at the end. Thanks to the TimeUSB company for providing me with this sample free of charge and for not telling me what to say or what to not say. I really only cooperate with such companies who understand that this is not an advertisement. This is a review done by a professional electrician, and as such I am obliged to do my work as best as I can. Referring to this, I have since made my testing process slightly better and constantly improving, and have optimized some measurement methods, so my future LiFePO4 LiFePO4 pack reviews are gonna be even more accurate, but still, I can sign under all that I have said in this video about this battery. Usually I do not put any of my subjective thoughts in these cooperation videos, but as this video will be watched by many people who sometimes even don't know how to interpret these numbers and data I just told, I am gonna sum it up in an easy to digest way. The TimeUSB webpage looks typically Chinese. It's a colorful webpage, some colorful stuff, some movement, some windows popping up, some flames somewhere, some icons, but it's normal in their country and it's that sort of mainstream marketing, so this really depends on you whether you like it or not. The battery design I consider unorthodox, as it has some colorful pictures on it, and I have never seen a battery with pictures. But I am fine with it. What could be added is some sort of manufacturer's tag with some quick reference data, some production label with voltage levels, with recommended and maximum currents, with temp ranges, etc. This data will come handy in future, and I would strongly advise on writing it on the battery itself. Talking about the battery itself, it can be summed up as being a higher mid-range battery pack. It has good quality cells, it's assembled very well, very safely, the wire thicknesses inside are okay, and the battery handles a nominal 1C current very much fine. The BMS is however a baseline model with just basic controller, no temp sensing and only temp fuses. The balancer, well, it is enough for most caravans and most some small FV systems, but it doesn't have much breathing room for that high load stuff. So if you would overload the battery very often, then the balancer may not be able to keep up. So it's a budget battery, very budget, built for reliability and built well. So that's it for this video. If you wanna see more electronics videos, feel free to look at my channel and please write some comments on how you liked the review and the battery. See you in another video, and until then, goodbye.